All right. So last time we started entering into this new realm of proving trig identities. So this is more, like I said, this is more of an algebraic endeavor. Up until this point, you've been looking at triangles a lot, curves of graphs, of trigonometric graphs and whatnot. We've been applying the law of sines, the law of cosines to triangles, right? Different kinds of triangles, not just right triangles. And then all of a sudden we just like transition into a aspect of trig that requires a lot of algebra involved. So this is like kind of a bit new when we talk about trig. So we'll continue with this. So we just touched upon it, right? We just touched upon what this idea is of proving trig identities. So we'll continue with this for now. So we started last time talking about simplifying trig expressions. And now what we're doing is we're given an equation that supposedly is a true statement, a true equation. And so what we have to do is algebraically show that the left-hand side of the equation is equal to the right-hand side of the equation. That is all we're doing for these for this kind of objective. So let's look at some. We've done one already last time, and we've done a couple of simplifying expressions, but we still have to get used to this new way of thinking. Okay, so look at this equation here. I got 1 over 1 minus sine squared theta. And I want to show that this equals 1 plus tangent squared theta. So you see this? This is an equation that I want to prove or show to be true. So my thing is show that this equation is true. So show that this is true. And obviously apparently we have a left-hand side, right? This is LHS, left-hand side, and we have a corresponding right-hand side. So either we show the right-hand side and we do algebra to get to the left-hand side, or we show that from the left-hand side, we apply some algebra steps to get to the right-hand side, or we show that we can simplify this, and if we simplify this, we get the same thing when we simplify. So either or. Sometimes one way is easier than the other. In this case, I'm going to start with the left-hand side, because the left-hand side is a bit more complicated. It's because you have a sine squared term in the denominator. What that tells me, or that leads me to believe, is that I could do something further to simplify. So I'm going to try to simplify the left-hand side. So I'm going to simplify the left-hand side. Okay, can anybody tell me what is the denominator? Also equal to. So this is where you have to go back to that list of trig identities that we talked about in the beginning. Remember, sine squared plus cosine squared is 1. That's the Pythagorean identity. And a lot of other identities stem from that identity. So does anybody know, what does 1 minus sine squared equal? Cosine squared. Thank you, Tiffany. Very good. So this is 1 over cosine squared theta, right? So remember, you have to remember these things. So recall that 1 minus sine squared theta equals cosine squared theta. So remember that. Now, remember, I want to go from the left-hand side and see if I can rewrite it as the right-hand side. So 1 over cosine squared theta, how else could I represent 1 over cosine squared theta? That might lead me to 1 plus tangent squared theta somehow. So 1 over cosine squared theta, what's another equivalent way to express that? When you have cosine in the denominator, when it's the reciprocal of cosine. What's the reciprocal of cosine? It's secant squared. 1 over cosine squared is secant squared. Now, what is secant squared? Isn't this 1 plus tangent squared? So you see, I have to recall again. Recall. What do I recall? Recall that one of the identities is that 1 plus tangent squared theta equals secant squared theta. Don't forget that. 1 plus tangent squared theta equals secant squared theta. So because I have secant squared theta, I can also represent it as 1 plus tangent squared theta, since this is an identity. And what did I just prove? What did I just show? So I put this little box here. It's like a little, it's like equivalent to what a period means, right? It's like the end. This is the end of the proof. I just showed that the left-hand side of this equation with some algebraic steps reaches the right-hand side of the equation. And so I showed that it's true. So this is what we're after, guys. This is what we're going to be doing from now on when we talk about proving identities. So any questions about this? So this is the idea. Same thing again. I want to show that this is true. So show that this expression is true. How do I show that? I got a left-hand side. And I want to show that this ends up being the right-hand side. You see that? The left-hand side looks a lot more complicated than the right-hand side. So let's start with the left-hand side then. What does the left-hand side say? We got 1 minus cosine squared theta multiplied by 1 plus cotangent squared theta. Now, what can we say about this? What could we do? There's two ways to go about this. Either you recall what these expressions are here, right? Individually, what they're equivalent to, or you can try to see what happens when I distribute or FOIL. But what is 1 minus cosine squared? What is this equal to? 1 minus cosine squared. It's equal to what? Sine squared theta. Thank you, Tiffany. Yes. This is sine squared theta. So recall again. This is all recall. 1 minus cosine squared theta equals sine squared theta. You have to remember these identities. So 1 minus cosine squared theta equals sine squared theta. And 1 minus sine squared theta equals cosine squared theta. So I can rewrite this now as sine squared theta. Does anybody remember or recall, what does 1 plus cotangent squared theta equal? So you see, these are a pair. You see, these are a pair that you should know. They should be paired up because they look very similar. They just switched the cosine and sine. And then there's another pair to this one. 1 plus tangent squared theta. 1 plus tangent squared theta equals secant squared theta. There's another one that you should recall. Recall that 1 plus cotangent squared theta, actually this equals cosecant squared theta. That's another one that you have to remember. And you can get all of these, like I said, you can get all of these from the Pythagorean one. If you know the Pythagorean, then you know like most of the identities that you need to know. They all really stem from this one. Sine squared theta plus cosine squared theta is 1. So I can write this as this now. Cosecant squared theta. So sine squared times cosecant squared. But what is sine squared times cosecant squared? When you multiply sine squared times cosecant squared, what do you get? Well, remember, what is cosecant squared? What is cosecant squared? It's 1 over sine squared. So sine squared and sine squared cancels. And I'm left with what? 1. And what is 1? 1 was the right-hand side. So the left-hand side equals the right-hand side. And I'm done. I finished. So that's the idea. The idea is to show the left-hand side equals the right-hand side. And I'll do 2 more of these, and then we can move on to the next thing. So what if I get this? So show that 1 minus cosine theta over, 1 plus secant squared theta over 1 plus tangent squared theta. Show that this equals 1 plus cosine squared theta. I want to show this to be true. So again, left-hand side, right-hand side, left-hand side. This equals 1 plus secant squared theta all over 1 plus tangent squared theta. So what can we do here? Look at the denominator, 1 plus tangent squared theta. Have I seen that before? I think we just talked about it, didn't we? 1 plus tangent squared theta. What is 1 plus tangent squared theta? It's secant squared theta. So I can rewrite this as 1 plus secant squared theta all over secant squared theta. Do you see that? So the bottom becomes, the denominator becomes secant squared theta. But again, I'm trying to find a way that I can simplify this, if possible, to get to the right-hand side. Now, the only thing I can do from here is to separate 1 over secant squared theta plus secant squared theta over secant squared theta. And then what is secant squared theta divided by secant squared theta? What is that? What does that reduce to? Anybody, what is something divided by itself? It's gonna be 1. Of course, Felipe, yes. This is 1. Anything divided by itself other than 0 is 1. Doesn't matter what it is. So secant squared theta divided by itself is 1. And then what is 1 over secant squared theta? Can I simplify this? What happens when I put 1 over the reciprocal of cosine, which is secant squared? So secant squared, guys, is, right? I'm going to write this as 1 over cosine squared theta. So I have 1 divided by a fraction, keep change flip, and when you flip the reciprocal of the denominator, when you flip this guy, when you flip it, you get cosine. You get cosine squared theta plus 1. But isn't this exactly the same thing as 1 plus cosine squared theta? And isn't this exactly the right-hand side? So I've just shown with a couple of algebraic steps that the left-hand side of my expression, when I apply some algebra steps here, I get to the right-hand side. So then the left-hand side must equal the right-hand side, and I have proven that to be true. Do you see that? And what I need to know for this, I need to know how to go from different expressions when I see them. So 1 plus tangent squared, now you have to make the match. You have to match this in your minds. 1 plus tangent squared theta equals secant squared theta immediately. Secant squared theta, what is that? That is 1 over cosine squared. And then from here to here, this is just algebra. It's just an algebra step. I have a fraction with a sum in the numerator. I can separate the numerators. I can separate the fraction, the single fraction, to 2 fractions. And then things work out. Things work out. Things cancel out very nicely, and then they become exactly what I'm expected to. So again, you're going to be given these kind of equations that are expected. You are expected to be able to show that the left-hand side equals the right-hand side. Okay, so one more of these. So let us show that 1 minus cosine of theta over sine theta plus sine theta over 1 minus cosine theta, this equals 2 cosecant theta. So again, left-hand side and the right-hand side. So I want to show that the left-hand side is equal to the right-hand side. And we did a problem similar to this in terms of simplifying. We did one last time. So we have 1 minus cosine theta over sine theta plus sine theta over 1 minus cosine theta. Okay, so look at the left-hand side. We have a fraction, 2 fractions, and we're adding them. But on the right-hand side, we just have one single expression. There's no addition. So what that leads me to believe is that I need to combine the fractions in some way. So when we add 2 fractions, we must have the same denominators, but we don't in this case. So what do? We find the LCD. And what would be the LCD between these 2 denominators? We did something like this last time. Anyone? What would be the LCD between sine theta and 1 minus cosine theta? Sine theta and 1 minus cosine theta. Thank you, Tiffany. That's right. That's all it is. It's sine theta multiplied by 1 minus cosine theta. Because they're just different terms, the least common denominator would just be a product of those 2 uncommon terms. And so now we have to do what? Now we multiply each fraction by the corresponding factor that it needs to create the LCD in the denominator. So sine theta here, what's missing? 1 minus cosine theta. So I have to divide by 1 minus cosine theta 1 minus cosine, I have to multiply, pardon me, by 1 minus cosine theta over 1 minus cosine theta. And then what's missing on this one? 1 minus cosine theta, I am missing a sine theta multiplied by sine theta. So you see, this is an algebraic step that I'm applying, okay? And when I do so, what happens? I get 1 minus cosine theta multiplied by sine theta in the denominator, and then I get 1 minus cosine theta multiplied by 1 minus cosine theta. The next fraction is 1 minus cosine theta multiplied by sine theta, and I get sine squared theta. So I get sine theta times sine theta. Great. Now, you see I have the same denominators. I have the same exact denominators. Because I have the same denominators, what can I do? Well, good thing I have the same denominators. Now I can just make it into a single denominator, which would be the denominator that I have. 1 minus cosine theta, and multiply that with sine theta. And then I need to do a bit more work here. So what I'm going to do is I'm going to put the 1 minus cosine theta multiplied by 1 minus cosine theta. I'm going to put that over here. I'm going to distribute. And I get 1 minus cosine theta minus cosine theta plus cosine squared theta, which reduces to 1 minus 2 cosine theta plus cosine squared theta. So that's what happens when you multiply this all out. And what do I get? I get 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. But what happens, what do you notice, or what should you notice about the expression in the numerator? There is something there that's called an identity that you all should know, that you should all remember. Cosine squared plus sine squared, thank you, Chen, that's right. It equals 1. It always will equal 1, always and forever. This equals 1. Great. So now I can replace that cosine squared theta plus sine squared theta expression. I can replace that with the equivalent 1. It equals 1. So that simplified a bit more the expression. I have less thetas now. And then I know that I can combine 1 with 1. 1 plus 1 equals 2. 2 minus 2 cosine theta over 1 minus cosine theta multiplied by sine theta. And then what else do I see? I see that, wait a minute, I got 2 minus 2 cosine theta. I got 1 minus cosine theta. So wait a minute, I can factor out the 2 in the numerator. Divided by 1 minus cosine theta multiplied by sine theta. 1 minus cosine cancels. And I got 2 over sine theta. And 2 over sine theta can be rewritten as 2 cosecant theta. And this is the right-hand side. This is a bit longer. This took a little bit longer to show that the left-hand side equals the right-hand side, but it was still possible. A bit more algebra was used, but not so much. It was just that we had to combine two fractions. That was really the whole crux of this. And once we were able to do that, we were able to figure out certain things that we should know, certain identities that we should have in our fresh in our minds. So remember, cosine squared plus sine squared will always equal 1. And then we were able to factor and simplify, and we were able to show that indeed the left-hand side, 1 minus cosine theta over sine theta plus sine theta over 1 minus cosine theta, that expression does indeed equal 2 cosecant theta. Okay? All right, any questions about this? Okay, so we talked about proving trigonometric identities, proving algebraic trigonometric expressions, how we're able to show that one side of the equation equals the other side of the equation. And I've mentioned to you all that now this is more of an algebraic flavor to trigonometry, and we'll continue on with this algebraic flavor. And in the next several minutes, we're going to be talking about certain formulas. So the first kind of formula that we're going to be considering are the sum and addition formulas. Sorry, sum and difference. So there's more formulas coming our way. Some difference formulas for trig. So the idea is, what happens to sine when I have a sum of two angles? So make believe I have a sum of two angles, A and B. So A and B are angles. What's the formula behind that? There is a formula. So the formula is the following: sine of the angle A multiplied by cosine of the angle B. Then I'm adding that to cosine of the angle A times sine of the angle B. So this is the sum formula for sine, and it is what it is. You can prove it that this is true, but we're not gonna consider that right now. We're just gonna be using these formulas. So sine formula for the sum is what we have here: sine A cosine B plus cosine A sine B. And then when I have difference, when I have, for example, A minus B, this is sine of A times cosine of B minus cosine A times sine B. So these are the sum formulas for sine. Sum and difference formulas for sine. Okay? So how can we use this? How is this applicable? Well, let me show you. For example, with this in mind, now I can, for example, find what is sine of 75 degrees. So I'm going to say find exact value of 75 degrees for sine. So you may be like, wait a minute, I can put that in my calculator, but the calculator doesn't give me an exact value. Remember, the word exact value means not approximate. It's exact. So it's not a decimal. It's some kind of fraction. It's some kind of radical expression, if possible. That's what it means to be exact. But then you're like, wait, but we only know sine of 60, sine of 30, sine of 45. And that's precisely how we're able to find sine of 75. Why is that? Because sine of 75, the number 75 is very nice because it comes from 30 plus 45, doesn't it? So doesn't sine, can't I rewrite this as 45 degrees plus 30 degrees? And then what happens? This becomes what? This becomes my A, and this becomes my B value. And then I have a sum formula. I'm using the sum formula for sine because I have a sum of angles. And then what does the formula show me? Sine of 45 degrees, multiply that by cosine of 30 degrees, plus cosine of 45 degrees times sine of 30 degrees. So that's my formula. I'm using it. Sine of 45 degrees, what does that equal? Rad 2 over 2. Cosine of 30 degrees, what does that equal? Rad 3 over 2. Cosine of 45 degrees, rad 2 over 2. Sine of 30 degrees, 1/2. Simplify. Rad 2 times rad 3, rad 6 over 4. Rad 2 over 2 times 1/2 is rad 2 over 4. So sine of 75 degrees is rad 6 plus rad 2 over 4. Or you can write it as rad 2 plus rad 6. It doesn't, the order doesn't matter when you add, and you can put that all over 4. So this is my exact value. If you plug this in your calculator, you would get exactly the same thing. Do you guys see that? Do you see how we're able now to find sine of other angles based upon the angles that we know? So once we have this, think about it. Once we have 75, then we can build. We can build up more angles from here. Okay, so now that we understand that, what happens, for example, if I want to find sine of 15 degrees? Is that possible? Let me see, 45. Yeah, that is possible, isn't it? Sine of 15 degrees can be rewritten as what? Sine of 45 degrees minus 30 degrees. The difference between 45 and 30 is 15. This becomes again A. This becomes again what? B. So now I use the difference formula for sine. What's the difference formula? It's exactly the same thing as the sum formula. The only difference is that the plus is a minus now. So I'm going to have sine of 45 times cosine of 30 minus cosine of 45 times sine of 30. What is sine of 45? Rad 2 over 2. What's cosine of 30? It's the same thing. Rad 3 over 2. Cosine of 45 degrees is rad 2 over 2. Sine of 30 degrees is 1/2. And so then I get rad 6 over 4 minus rad 2 over 4. So sine of 15 degrees, that equals rad 6 over 4 minus rad 2. Everybody with me on this? This is the exact value. Thank you, Felipe. Appreciate it. Okay, so we're just using a formula that we're now have come across, which is the sum and difference of sine. And so then the question might be, what about cosine? And of course, cosine has its own formulas as well. So that's for sine. Now let's look at cosine. Thank you, Tiffany. You see, you guys are beyond. You guys are on it. That's right, Tiffany. That's right. It should be a 4, not a 2. Pardon me. It should be same denominator if you have the same denominators. Now, what happens if I have cosine of a sum instead? And then what happens if I have cosine of a difference instead? So cosine of a sum gives you what? Cosine of A, cosine of B, and now this is when it kind of flips. Instead of adding, you subtract. So it's kind of the opposite. If you have a sum, you're going to subtract for cosine. If you have a sum, and for sine, then you're going to have a sum in between. But cosine is the opposite. And you notice here, I have cosine of A and cosine of B. And then I get sine of A, sine of B. And then cosine of A minus B, I get the same thing. Cosine A, cosine B, plus sine A, sine B. So these are the sum and difference formulas for cosine. So with this in mind, I can figure out, for example, what is cosine of 75 degrees. So it's the same idea as finding sine of 75 degrees. We know that cosine is what? 45 plus 30 degrees, correct? So we know that. And this becomes cosine of 45 times cosine of 30 minus sine of 45 times sine of 30. Again, I'm just using the formula that I have above. And this looks very similar to what we've done already for sine. Remember cosine of 75 degrees? It's going to come out to look like sine of 15 degrees because they're complementary angles. 15 and 75 are complementary. So sine of and cosine of complementary angles are equal. So we're already going to expect that. This is rad 2 over 2 multiplied by rad 3 over 2 minus rad 2 over 2 multiplied by a half. This is exactly the same thing. Rad 6 over 4 minus rad 2 over 4, which is rad 6 minus rad 2 over 4. And this is my expression. 6 minus rad 2 over 4, which is the same thing as sine. So note, sine of 15 degrees equals cosine of 75 degrees, which equals rad 6 minus rad 2 over 4. And you notice that 15 and 75 are both complementary. They're complementary angles. Okay. So that's pretty much using the sum and difference formulas for cosine and sine. Okay, great. Now, how do I do this? How do I do cosine of 195 degrees? I need to find two angles that add up to 195 degrees that I would know the values of. So 195. What adds to 195 or subtracts to 195 that I know the values of? So for this, you have to think about the following. You have to think about the angles. So think about 30 degrees, 45 degrees, 60 degrees, 90 degrees. And then you have to look at the multiples. Think about 35 and its multiples. So for example, the multiples of 30 are what? 60, 90, of course, and then 120, 150, 180, 210, so on and so forth. 45 is 45, 90, 135, so on and so forth. 60 is 120, to 180, right? So on and so forth. And then you see, these are the angles that I need to have in my mind, because if I know these, I know these as well. I know the values for the trig functions for these as well. Now, which one of these numbers, when I pair them up, add up to 195? Chen, 150 and 45. Yeah, or 135 and 60. So Sydney and Chen, you both used correct numbers. So you know what? Let's do both and see if we do get the same thing. So I'm going to do it one way. So the first way, I'm going to do this. I'm going to say cosine of 195. That's the same thing as saying cosine of 135 plus 60. By the formula, I get cosine of 135 times cosine of 60 minus sine of 135 times sine of 60. That's according to the formula. Now, what's cosine of 135? What would be cosine of 135 degrees? Remember, the way we evaluate this is to first figure out where is 135 degrees? What quadrant? It's in quadrant 2. If I'm in quadrant 2, cosine is what? Negative. So I'm sure I'm going to have a negative. What is cosine of 135? I have to refer to the reference angle. The reference angle of 135. Well, where did you get 135 from? It's 45 degrees. Cosine of 45 degrees is rad 2 over 2, so I know this will be negative rad 2 over 2. Cosine of 60 degrees is 1/2. Sine of 135 degrees, do the same exact thing. 135, second quadrant, sine is positive. Sine of 45 degrees is rad 2 over 2. That negative sign started from the beginning to be there, so I can't change it because sine of 135 is just rad 2 over 2. Sine of 60 is rad 3 over 2. So what's my final answer? Negative rad 2 over 4 minus rad 6 over 4. And I can write this as negative 2, negative rad 2 minus rad 6 all over 4. So cosine of 195 degrees is negative rad 2 minus rad 6 over 4. I expect it to be negative because 195 is in the third quadrant and cosine is negative in the third quadrant. So it makes sense that it's negative. Now I want to show you that I can also use the other pair of angles that was suggested by Sydney. So I'm going to use 150 instead. Cosine of 150 plus 45 degrees. This tells me by the formula that this will be cosine of 150 degrees multiplied by cosine of 45 degrees minus sine of 150 degrees times sine of 45 degrees. So what is cosine of 150 degrees? Same thing, right? What quadrant is 150 in? 150 is in quadrant 2. Cosine is negative in quadrant 2. Reference angle of 150 is 30. So cosine of 30 will be negative rad 3 over 2. Cosine of 45 degrees is rad 2 over 2. Minus sine of 150. Second quadrant, sine is positive in second quadrant. The reference angle is 30. Sine of 30 is a half. And this is rad 2 over 2. What do I get? I get negative rad 6 over 2 minus rad 2 over 2, over 4. And this becomes negative rad 6 minus rad 2 over 4, which is exactly the same thing. It's exactly the same thing as what we did above. I just switched the order of rad 6 and rad 2, but they're both negative, so it doesn't really change the value. So very good. I just demonstrated to you guys that as long as you have two numbers that add up to 195, it doesn't matter what they are, as long as you're able to do so and you know the values of those angles that you choose. So in this case, 135 plus 60 adds up to 195. I found it using the formula. 195 can also be written as 150 and 45. And I used the same formula and I got the same answer. Okay? Okay. Awesome. Next. Now, we've been doing a lot of degree stuff, but of course, we can't forget radians. So what if I have radians instead? So this is when it gets a little bit more complex. 19 pi over 12. How do we get to that? So now I have to do the same exact thing that we did, right? Same exact thing. We have to think about the angles that we know, but now in radian mode. So think about pi over 6, pi over 4, pi over 3. We got to think about those. And then we have to think about the multiples. 2 pi over 4, which is equal to pi over 2. 2 pi over 6, which equals pi over 3. 3 pi over 6, which is pi over 2. 4 pi over 6, which is 2 pi over 3. 5 pi over 6, so on and so forth, right? Same thing here, 2 pi, right? Then we have 3 pi over 4. Then we got pi. We got 2 pi over 3, and so on and so forth. So which one of these numbers, when you add them, give me 19 pi over 12? So it's not going to be so apparent. You may have to try and figure it out and be like, maybe this one works, maybe that one works. So you have to notice, right? So for example, let's just do a little quick example. Pi over 3 plus pi over 4. What does that give me? Well, I have to make the same denominators. So I got 4 pi over 12 plus 3 pi over 12. It's 7 pi over 12. So you see how it would make sense to use one of these two pairs or multiples of those pairs? Because I get a 12 in the denominator. If I were to add these, I would also get a 12 as well, actually. So for example, if I do pi over 6 plus pi over 4, I can multiply this by 3, I can multiply this by 2, and I get 2 pi over 12 plus 3 pi over 12. That equals 5 pi over 12. So you have to be careful with that. So it could be one of these. It could be a pair of these or a pair of these. So what do you guys think? What two numbers here, what two radian angle measures will add up to 19 pi over 12. Or maybe you have to subtract. Anybody has any idea? No. 19 pi over 12. How can I separate 19 pi over 12 as two fractions? That may or may not help. Can I do this? 21 pi over 12 minus 2 pi over 12. Does this reduce anything that's nice for me? Well, look at this. I can rewrite this as pi over 6. So that checks out, right? Because this pi over 6, I know pi over 6. And then how about 21 pi over 12? I can divide both by 3, and I get 7 pi over 3. And 7 pi over 3 is a multiple of pi over 3. So I know it's not that apparent. You have to kind of think about this a bit more. So I can rewrite this as sine of 7 pi over 3 minus pi over 6. And again, it doesn't have to be a difference. It could be, so pardon me, wouldn't it be pi over 4 divided? Yes, of course. What am I saying? You're right. It's 7 pi over 4. So actually it would be a multiple of pi over 4. And again, these angles here could be different. Or they could be a sum. So you have to find yourself what two angles would work. And it's harder when it's radians because it's less intuitive, right? We're more accustomed to degrees, but it's still possible. So are we in agreement? 21 pi over 12 minus 2 pi over 12, that gives me 19 pi over 12. What's good about this is this reduces to one of the ones that I know, one of the multiples that I know, which is 7, which is pi over 4. And the other one reduces to something pi over 6. So I know these. I can find these myself. So let's find it. So what's sine of 7 pi over 4 minus pi over 6? Well, I have a and b, don't I? So then I have to use my formula for sine. So go back to sine. Remember, sine of a minus b equals sine of a cosine of b minus cosine of a sine b. So this will be sine of 7 pi over 4 times cosine of pi over 6 minus cosine 7 pi over 4 times sine of pi over 6. And if you really find difficulty with radians, what you could do is just take 19 pi over 12, convert it to degrees, and then work from there. Work with degrees. And I think that might be a bit easier if you don't see the whole radian version of this. So you can take this, convert it to degrees, and then work your way with that. So what is 7 pi over 4? Where is 7 pi over 4? 7 pi over 4 is in the fourth quadrant. Sine is negative. So this will be negative, and the reference angle of 7 pi over 4 is pi over 4, so it's negative rad 2 over 2. Cosine of pi over 6 is 30 degrees. Cosine 30 degrees is rad 2 over 2, rad 3 over 2, pardon me. Minus cosine of 7 pi over 4. 7 pi over 4 is in the fourth quadrant. Cosine is positive. Reference angle is pi over 4. This would be rad 2 over 2. And what is sine of pi over 6? It's a half. Because sine of 30 degrees. This will equal what? Negative rad 6 over 4 minus rad 2 over 4. Which is negative 6 minus rad 2 over 4. And that is your answer. So you're going to be seeing a lot of this. The rad 6 over 2 with rad 6 with rad 2 over 4. A lot of those. Either they're going to be negative, positive. It's because they're using the same angles. Sine, 45 degrees, 30 degrees, and so on. Okay, are we good with this? We're good with this? Okay, I'll give you 2 more of these kind of examples, and then we'll move on to a new set of formulas that you must know. Okay. Now, so using some difference formulas, find the value of given expression. So look at this. I want to know what this equals. Of course, you can put in your calculator, but there's a certain structure behind this, an algebraic structure or formula that we've just discussed. So what do you notice? Sine of 18 cosine of 27 plus cosine of 18 times sine of 27. What does this look like? This is my A, this is my B. This is my A, this is my B. And this is B of what? Sine, cosine, cosine, sine. What is this? What is sine of A cosine of B plus cosine of A sine of B? What does that equal? Well, doesn't it equal the sum? Sine of A plus B? Isn't that what the sum is? So sine of 18 cosine of 27 plus cosine of 18 times sine of 27. This actually equals sine of 18 plus 27, doesn't it? That's the formula. But what is sine of 18? What's 18 plus 27? 45. And don't we know sine of 45? Of course. Rad 2 over 2. That's it. So sine of 18 times cosine of 27 plus cosine of 18 times sine of 27 is exactly rad 2 over 2, because this is just hiding, or sine of 45 degrees is hidden behind this expression. Because it's a sum. It's a sum formula for sine. And then another one here. Cosine of 3 pi over 7 times cosine of 2 pi over 21 plus sine of 3 pi over 7 times sine. What is this? I got cosine of 3 pi over 7 times cosine of 2 pi over 21 plus sine of 3 pi over 7 times sine of 2 pi over 21. Cosine of A times cosine of B plus sine of A times sine of B. That's what I have. And what is cosine of A times cosine of B plus sine of A sine of B? What does this equal? Difference. Thank you, Tiffany. Cosine of A minus B. So this whole thing equals cosine of 3 pi over 7 minus 2 pi over 21. And now I have to subtract two fractions. How do you subtract 3 pi over 7 minus 2 pi over 21? I must have the same denominator. So 7 and 21, the least common multiple is 21. So I must multiply this by 3 over 3. When I do so, I get cosine of 9 pi over 21 minus 2 pi over 21. Same denominators, subtract the numerators. 9 pi minus 2 pi is 7 pi over 21. 7 goes into 21 3 times, so this is equal to cosine of pi over 3. Cosine of pi over 3 is the same thing as saying cosine of 60 degrees. Cosine of 60 degrees is 1/2. So this whole long expression that I had in the beginning, it really just equals 1/2. So I was able to recognize that. I was able to recognize the structure, that it was the difference formula for for cosine. And once I have that, then so in a sense, what's happening is I'm recognizing the formula and going backwards with the formula. So normally we get a sum and then we use the formula to find the result. Now we kind of start from the result end, or the formula, right, that we use, and we're going back to our original sum or difference of two angles. So that's the sum and difference formula for cosine and sine. So a lot more formulas are coming your way. In particular, we're going to be talking about what are called the double angle formulas. Now, the double angle formulas really are just formulas based upon the sum and difference formulas. So let's look at the double angle formula for sine. So what do I mean by double angle? I mean that I'm taking sine of twice the angle. Sine of 2 theta. There's a formula for this. Now, to get to that formula, I need to remember 2 theta. What is 2 theta? Isn't it theta plus theta? So theta plus theta, that's the sum formula for sine. And what's the sum formula for sine? It's sine theta cosine theta plus cosine theta sine theta, right? In this case, my A and B are the same. They're thetas. But sine theta cosine theta is the same thing as cosine theta sine theta. So actually, sine of twice the angle is equal to 2 times sine theta times cosine theta. That's one of the formulas for sine. Sine of twice the angle is 2 sine theta cosine theta. So anytime you see 2 sine theta cosine theta, think of sine 2 theta. Anytime you think of sine 2 theta, think about 2 sine theta cosine theta. That's a new formula. This is a double angle formula for sine. And this is the easier kind. The harder one, or I wouldn't say the harder one, it's just the more involved one, is cosine of twice the angle. What is cosine of twice the angle? Well, it's the same idea, isn't it? Same principle. Cosine of theta plus theta, because 2 theta is theta plus theta. So I have the sum formula for cosine. The sum formula of cosine looks like the following. It's cosine theta times cosine theta minus sine theta times sine theta. Cosine theta times cosine theta is cosine squared theta. Sine theta times sine theta is sine squared theta. So cosine of twice the angle is equal to cosine squared theta minus sine squared theta. remember, cosine squared theta plus sine squared theta is 1. But cosine squared theta minus sine squared theta is not 1. It's cosine of twice the angle. Now you're like, wait, but you just said it's more involved. It is. Why is it more involved? Because of the following. Recall. What do I have to recall again? I have to recall that cosine squared theta is equal to 1 minus sine squared theta. I have to recall that sine squared theta equals 1 minus cosine squared theta. So actually, there's 3 versions for this one. You have 3 versions. So one version is if I replace cosine squared theta with 1 minus sine squared theta. And the other version is if I replace sine squared theta with 1 minus cosine squared theta. So if I do so, look what happens. Cosine of twice the angle, instead of writing cosine squared, I'm going to write 1 minus sine squared theta minus sine squared theta. So what's 1 minus sine squared theta minus sine squared theta? It's 1 minus 2 sine squared theta. So cosine of twice the angle can also be written as 1 minus 2 sine squared theta. Or I can replace, instead of cosine squared theta, I replace sine squared theta. So what happens when I do that? Cosine of twice the angle is equal to cosine squared theta minus parentheses 1 minus cosine squared theta. And then I distribute the negative sign and I get cosine squared theta minus 1 plus cosine squared theta. But cosine squared plus cosine squared theta is 2 cosine squared theta minus 1. So this is my other version. So look at this. You have 3 versions for cosine 2 theta. You have the version that has cosine and sine together, which is cosine squared theta minus sine squared theta. That's the first one. Then you have the version where you have only sine in it, which is 1 minus 2 sine squared theta. So if you have sine only, you can still find cosine of twice the angle. And then if you only know cosine theta, you can still find cosine 2 theta, which is equal to 2 cosine squared theta minus 1. Sine is easy because you only have one version. Cosine, you have 2. Okay? Awesome. This is when it gets good, guys. So you have to know these now. And I think that's all the formulas, guys. These are all of them. So you need to know the identities, Pythagorean identity, cosine squared theta plus sine squared theta equals 1. And all the identities that fall from that, which is sine squared theta, right? Sine squared theta equals 1 minus cosine squared theta. Cosine squared theta is equal to 1 minus sine squared theta. 1 plus tangent squared theta equals secant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. So all those identities really fall under one category, which is the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. Then you need to know the sum and difference formulas for cosine, which are these two, and for sine, which are these two. So you have to know those formulas as well. And then just for now, just for this class, you need to know double angle formulas. For sine 2 theta, I got 2 sine theta, cosine theta. That should be synonymous. So these should be synonymous in your heads. And then for cosine twice the angle, you have 3 versions of them. And there's more formulas, guys. There's a half angle formula. There's the sum to product formulas, product to sum formulas. So the number of formulas that you get from trig really can make your head spin. But for this class, you don't need to know any more. This is it. Double angle formulas. Okay? So I don't know if that's a relief or still a bit cumbersome to know all these formulas. So let's see this in action. So let's see this. Find sine of twice the angle, cosine of twice the angle, and tangent of twice the angle if you know that sine, so another thing, to know cosine, to know tangent, there's also a formula for tangent, but if you know sine and cosine, then you know tangent. So it comes right up, comes right out. If you know that sine of theta is equal to 5/13 and theta is in quadrant 1. Okay, so this is, we're gonna start basic. We're gonna start off slow. So if I know that sine of theta, if I know sine of theta is 15/13, 5/13, pardon me, then I can create a triangle that's a right triangle. One angle is theta, and I can fill out the sides. This is what? Opposite, hypotenuse. So the opposite side would be 5, the hypotenuse would be 13, and what's the missing side? What would be the missing side of a triangle that has one side 5, the other side 13? You can use a Pythagorean theorem, or you can remember that this is a Pythagorean triple. And Tiffany, you're on fire today. 12, that's right. Thank you, Sydney. That's right, it's 12. So I know all the sides. Now, I want to find sine of twice the angle. Well, what is sine of twice the angle? It's twice the sine theta times cosine theta. And I could just read off from the triangle. Sine of theta, I already know what sine of theta is. They give it to me already. It's 5/13. Now, what's cosine of the angle? Theta. Well, 12/13 is the adjacent over the hypotenuse side, which is 12/13. Multiply. 2 times 5, 10 times 12 is 120. 13 times 13 is 169. I did it. So sine of 2 theta is 120/169. Good. Done. Next. What's cosine of twice the angle? Now you can choose yourself. I have 3 ways to get it. I got 3 different ways. Doesn't matter which way you choose. You get the same answer. So I can do sine and cosine together. If you want to do that, you can do that. So this becomes cosine squared theta minus sine squared theta. What is cosine? It's 12/13 squared. What is sine? 5/13 squared. What's 12/13 squared? It's 144/169 minus 25/169. What's 145 minus 25? 145 becomes what? This becomes 9. And then this becomes 11. So the answer is 119/169. So sine of twice the angle is 120/169. Cosine of twice the angle is 119/169. And what is tangent of twice the angle? But tangent is sine of twice the angle over cosine of twice the angle. So what's sine? 120/169. What's cosine? It's 119/169. What happens when you have a fraction divided by fraction? You multiply by the reciprocal. 120/169 multiplied by 169/119. The 169s cancel, and I'm left with 120/119. That's tangent. And voila. Voila. Any questions about finding sine 2 theta, cosine 2 theta, tangent 2 theta, if I know just 2 things, sine theta and where the angle is? We're good with this? Okay. Now let's do something a bit. So this is like a basic version of these kind of problems. Now let's do the same thing. Find sine of twice the angle, cosine of twice the angle, tangent of twice the angle. Now this is if tangent of theta is negative a third. Uh-oh. And cosine is less than 0. Okay, we have to work a bit more for this one. The one in the previous answer problem was easier because we're all in the first quadrant, so everything's positive. And 5, 12, 13 is a Pythagorean triple. We're not going to have a Pythagorean triple, and we don't know what quadrant we're in. We're not going to be in the first quadrant because tangent is negative. So first thing we have to do is figure out where is theta. What quadrant is theta in? Well, let's look at tangent. Tangent is negative. Where is tangent negative? What quadrants is tan negative? 2 or 4. So quadrant 2 or quadrant 4. Good. And then how about cosine? Where is cosine negative? 2 and 3. Good, Jen. So then what quadrant is theta in? It has to be quadrant 2. So that's important. So the only trig function that's positive in quadrant 2 is sine. Okay, once we establish that, now we make the right triangle. What's the right triangle? Can't draw a triangle. So what's the right triangle? Theta. What's opposite theta? 1. Because remember, this is opposite adjacent, right? The adjacent side is 3. Forget about the negative for now because I already know what quadrant I'm in. I'm supposed to get a negative for tangent because I'm in the second quadrant. Now I have a triangle where I have one side being 1, the other side being 3, but I'm missing the hypotenuse. So what would be the hypotenuse? How would I get it? It's not a Pythagorean triple, so I won't be able to recall it from memory. So how do I find that missing side, the hypotenuse side? If you don't know a side of a right triangle, you have to use the Pythagorean theorem. So if this is x, for example, what do? I write 1 squared plus 3 squared equals x squared. 1 plus 9 equals x squared. 10 equals x squared. X is equal to rad 10. Oh, that's a good question, Daniel. When do we know what negative? So one thing I just want to, this is just a separate aside, right? This is just a separate, this is a side note here. If you got negative 1 over 3, that's equal to negative 1/3. That's equal to 1 over negative 3. They're all the same. So either or, Daniel, you can choose whatever number you want to be negative. Either the 1 is negative or the 3 is negative. It's still the same thing. That negative sign can move from the top to the bottom. So either or. But that's why I don't, when I make the triangle, I don't have negatives. I don't use negatives because first of all, when we talk about triangles and side lengths, we could never talk about a negative side length. That doesn't make any sense. The negative is just indicating to me where theta is. Theta could be quadrant 2 or 3 or 4 because tangent is negative. Cosine is also negative, so it's either in quadrant 2 or 3. But because I want both of these statements to hold together, to be true together, then it must mean that theta must be in quadrant 2. So once I establish the quadrant that theta is in, I don't have to worry about the negative any longer, right? Yes, that's right. Sine is positive. That's correct. So now what I'm interested in is given a right triangle with these dimensions 1 and 3 as the opposite and adjacent side, what would be the hypotenuse of such a triangle if I were to create one? Well, it's going to be rad 10. So now once I know this, I can find everything. I can find sine of twice the angle. What is sine of twice the angle? Well, it's 2 times sine of the angle times cosine of the angle. Now remember, sine is positive in the quadrant 2. And what is sine? Sine is opposite hypotenuse. So this would be 2 times 1 over rad 10. What's cosine? It's 3 over rad 10. But cosine is what? Negative in the second quadrant. So what's going to be my answer? Negative 6 over 10, because rad 10 times rad 10 is 10, which equals negative 3/5. So sine of twice the angle is negative 3/5. You see how we're doing this? And then the next one, cosine of twice the angle. So we used the first version for this one, right? Cosine squared minus sine squared. I'm going to use another version. I'm going to use the sine version. 1 minus 2 sine squared theta. What is this? This is 1 minus 2 times what sine? Sine is 1 over rad 10. I square it. So this becomes 1 minus 2 times 1 over 10. This is 1 minus a fifth, 4/5. Cosine of 45 degrees. Wait, cosine of 45 degrees. Cosine of twice the angle is 4 over 5. Positive. Okay, and then once we have that, tangent, what's tangent? Tangent is just sine of twice the angle over cosine of twice the angle. Sine of twice the angle is negative 3/5. Cosine of twice the angle is 4/5. You keep, you change, you flip. 5's cancel. What's the answer? Negative 3/4. You see that? Once we establish the fact that theta is in a certain quadrant, and once you establish the right triangle with the right dimensions, then everything else is just use formula, plug in, find answer. Okay? Okay, we're good with this. This is the extent of these kind of problems. I know it's a lot of formulas, guys, for today. A lot. It's just coming straight to you guys. 100 miles an hour. Okay, now once we have that, we have 2 more things to discuss. Hopefully we have enough time to do both of them. So once we have the double angle formulas, I want you to find the exact value now. Find exact value of trig expressions. Now, this is when we have inverse trig that pops up again. Yep, inverse trig makes an appearance again. So what is sine of twice cosine inverse of 7 over 25? Now, I told you these things get interesting. It's more interesting now. Now we have inverse trig pops up again. You're like, what? I thought we're done with that. Nope, coming back. Now, what is cosine inverse of 7 over 25? I don't know. But what I do know is that this equals theta. It's an angle, right? That's what inverse trig does. It gives you angles. So in a sense, I have this. Look, sine of twice theta. But hey, I know what sine of twice theta is. It's 2 sine theta times cosine theta. Right? So let me unpack this a bit. Let me unpack cosine inverse 7 over 25 equals theta. Let me unpack that. How can I rewrite this? Remember when we talked about rewriting it without inverse trig? I can rewrite this as cosine theta equals 7 over 25. But what is a right triangle with these dimensions? What is the adjacent side? Hypotenuse side. So this side here that's adjacent is what? 7. The hypotenuse is what? 25. Now, do you guys remember what is the Pythagorean triple that has 7 and 25? If you don't remember, you can do the Pythagorean theorem, but if you do, this is 24. That's right. Of course, not drawn to scale. Not drawn to scale. Now, once I have the right triangle, guys, I got everything. Sine of theta is what? Opposite over hypotenuse, which is 24 over 25. Cosine of the same angle, well, we have it already, right? Is adjacent over hypotenuse. And then 25 times 25 is 625. And then I have to use 2 times 24 times 7. And I get 336. So sine of this strange expression in here, twice of cosine inverse of 7 over 25, that's the same thing as saying 336 over 625. That's the answer. Okay, let's do a few more of these with inverse trig. So this is find exact with trig expressions. And this is particularly with inverse trig. What if I get this now? Cosine of tan inverse of 12 over 5. Sorry, cosine of twice that. Same idea, guys. Same idea. This equals theta. So really what I have is cosine of twice theta. And cosine of twice theta, I can rewrite it in 3 different ways. It depends on which way you desire, prefer. I've done the cosine squared theta minus sine squared theta version. I've done the 1 minus 2 sine squared theta version. So now I'm going to use the cosine squared version. 2 cosine squared theta minus 1. That's the other third version for cosine of twice the angle. Okay, so I'm going to use this. Now let me unpack the idea that I have theta. So what do I have? I got tan inverse 12 over 5 equals theta. So I can rewrite, let's rewrite this as tan theta equals 12 over 5. Opposite, adjacent. What do I do? Right triangle. Oops. Call this theta. What's the opposite side in this triangle? 12. What's the opposite side? What's the adjacent side? 5. 5, 12, and what's the missing side then? What's the hypotenuse? 13. That's it. You see, now you guys are instinctively saying that. 5, 12, 13. Great. Now that I know that, don't I know cosine theta? What is cosine theta? Adjacent over hypotenuse. So this is 2 multiplied by 5 over 13 squared minus 1. 5 squared is 25. 13 squared is 169. 2 times 25 is 50. 50 over 169 minus 1. Same denominator, so I can rewrite 1 as 169 over 169. 50 minus 169 is negative 119 over 169. And that's my final answer. So in the beginning, it looks complicated. This looks like, what in the world? And then you have to be like, Well, this is theta angle. So I know cosine of twice the angle. This is double angle formula. I have 3 versions of this. Choose one. Then what you have to do is take this and unpack this using the right triangle. Rewrite this without the inverse trig, so I can rewrite it as such. And then from here, I can construct a right triangle that has these sides as the dimensions that are supposed to correspond with tangent, opposite over adjacent. And then I realize that this is another Pythagorean triple, so 5, 12, 13. And once I have this right triangle, I can from here deduce that cosine of the angle must be 5 over 13. And once I have that, plug in the formula and you do the arithmetic, and you find that negative 119 over 169 is the value of cosine of twice the tan inverse of 12 over 5. Woo, 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 woo. Crazy, right? Crazy stuff. Crazy stuff. Okay, one more of these, one more, and then we're gonna move on to more proving. We're gonna prove more stuff now because now we're gonna use double angles. What if I have this now? Secant of sine in, sorry, secant. What? No, no, not secant. Yeah, let's do cosine. Sorry, cosine of twice sine inverse of 1/4. What does that equal? Same thing, guys. Take the inverse trig, call it theta. What is this going to be? Cosine of twice theta. What is cosine twice theta? I'm going to use sine for this, okay? So it's 1 minus 2 sine squared theta. Unpack theta. Sine inverse of 1/4 equals what? Theta. Rewrite this. Sine theta equals 1/4. Use a right triangle if you need it. What is the right triangle going to be? Theta, right angle. Opposite is 1, hypotenuse is 4. And what's the missing side to this? If you got 4 hypotenuse, 1 in the adjacent side, the opposite side, what would be the missing side? Using the Pythagorean theorem. Call this x. I got 1 squared plus x squared equals 4 squared. 1 plus x squared equals 16. X equals 15. X squared equals 15. So x is square root of 15. So this is square root of 15. But the cool thing is, all I need to know for this one is all I need to know is sine of theta. But I know sine of theta. It's a fourth. So I'm actually pretty good with this. This is 1/4 squared. 1 minus 2 times a 16 is 1 minus an eighth. 1 minus an eighth is 7/8. So cosine of twice sine inverse of 1/4 is 7/8. Okay. 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 Great. We're doing a lot here. Okay, so now I want to evaluate. Inverse trig expressions again. Using double angle. So it's kind of the same thing we've done already. But now we're just more specific. We're not going to find all 3 double angle formulas. We're just going to find one. So find cosine of twice the angle if I know that sine of theta is -3/5 and theta is in quadrant. Theta is in quadrant 3. So I want to know cosine of twice the angle. Actually, this is not that bad because if I know sine of theta, then I should use the version that only has sine of theta in it. So I should use 1 minus 2 sine squared theta, which is 1 minus 2 times -3/5 squared, which is 1 minus 2 times 9 over 25, which is 1 minus 18 over 25, which is 25 over 25 minus 18 over 25, which is 7 over 25. So I got that cosine of twice the angle is 7 over 25. This is very similar to what we did in the very beginning of this segment of double angle formulas, right? We had to find cosine of twice the angle, sine of twice the angle, tangent of twice the angle by knowing one thing about the angles. We did this here. Yeah, something like this. We did this already, but now we're just like specifying, oh, I just want one of them instead of all three. So that's the only difference with this. So we've done this already. Okay, now we're getting to the more difficult part, I would say, of double angle is proving trig identities. So I want to prove trig identities with double angle this time. So now the trig identities are going to be more complex because of the double angle aspect. So proving trig identities using double angle formulas. So I want to show, for example, I want to show that sine theta plus cosine theta, when I square this, this gives me 1 plus sine twice. Sorry, this gives me sine of twice theta. I want to show this. Remember, we started with proving identities. How do we prove identities? Left-hand side, make sure that equals the right-hand side. So what is the left-hand side? The left-hand side is sine theta plus cosine theta squared. What is sine theta plus cosine theta squared? I need to square them. So I need to multiply sine theta plus cosine theta, multiply that with sine theta plus cosine theta. So what do I do? FOIL. Sine times sine is sine squared. Sine theta plus cosine theta is sine theta cosine theta plus cosine theta sine theta plus cosine squared theta. Sine theta plus cosine theta cosine theta plus cosine theta sine theta, they're the same two terms. So we have 2 sine theta cosine theta plus cosine squared theta plus sine squared theta. But let me rearrange this. Sine squared theta plus cosine squared theta plus 2 sine theta cosine theta. What is sine squared theta plus cosine squared theta? What is that equal to? This should be immediate. It should be what? One of the Pythagorean, the Pythagorean identity. Sine squared theta plus cosine squared theta. That's right, Yue. It's 1. And then wait a minute. What's 2 sine theta cosine theta? Didn't we just discuss this a lot the past half hour? What's 2 sine theta cosine theta? What is that equal to? Isn't that exactly sine of twice the angle? And wait a minute, isn't that exactly the right-hand side? So didn't I just show that the left-hand side actually ends up being the right-hand side? So all it is now that you know double angle formulas, you have to be able to perceive, wait, this is double angle for sine. You have to be able to identify, find it, identify the double angle. Okay? So there's tons of these. Tons. What if I get this? Show that 1 minus cosine of twice the angle over sine of twice the angle, this equals tangent. Again, I got left-hand side, right-hand side. So let's start with the left-hand side because it looks more complicated. So we have to simplify the left-hand side. The left-hand side says 1 minus cosine of twice the angle over sine of twice the angle. Now, the only thing I can do in the denominator is rewrite it as 2 sine theta cosine theta because I know that's cosine of twice the angle. Now, the problem lies in that cosine of twice the angle has 3 different versions. So, for example, if I choose the version that I do 1 minus cosine squared theta minus sine squared theta. If I do this, right, it may give me a way to get to the answer, or it may not. So let's check. What happens if I do that? I distribute, I get 1 minus cosine squared theta plus sine squared theta all over 2 sine squared theta cosine, sorry, not cosine, sine theta cosine theta. So again, what did I do? I got cosine twice the angle and rewrote it as cosine squared theta minus sine squared theta. That's one of the versions for cosine twice the angle. I distributed the -1 because it's in the parentheses. Make sure you keep that in parentheses. When I distribute that -1, I get 1 minus cosine squared theta plus sine squared theta. Now, what you have to recognize is, wait a minute, I know this. What is 1 minus cosine squared theta also equivalent to? It's equivalent to sine squared theta. But what's sine squared theta plus sine squared theta? It's 2 sine squared theta. But what happens? 2's cancel. Sine, one of those cancels with one of the signs here because I have sine squared in the numerator and I got 1 sine in the denominator. So then one of the signs are canceled out. And what's left? Sine theta over cosine theta. But what's sine theta over cosine theta? Tangent theta. And what is tangent theta? The right-hand side. So I could have used the other ones. And I'll probably have to do the same exact idea. So either of the other two would also have worked. You just have to simplify it in a different way. But when you simplify it, you will always get down to this sine theta over cosine theta, which is tangent theta. We do have 2 minutes. Thank you, Felipe. Thank you. Is that enough time for another one? We can do another one real quick. Real quick. So I want to show, what do I want to show? 2 tan theta over 1 plus tangent squared theta. This equals sine of twice the angle. Again, we got the right-hand side, we got the left-hand side. What does the right-hand side say? I got 2 tan theta over 1 plus tan squared theta. So again, with this 1 plus tan squared theta. This here, 1 plus tangent squared theta, is secant squared theta. Sine of is right or left? Sine of 2 theta. I don't know what you mean by right or left. Oh, sorry. I don't know my right hand between my left hand. That's my mistake. You're right. I went too fast. So this is the left hand. This is the right hand. That's what you meant. Yeah, sorry. This is the left hand. Okay, and then what? I can rewrite this as what? 2 times sine theta over cosine theta divided by 1 over cosine squared theta. I'm going to rewrite it using sines and cosines. This becomes 2 sine theta over cosine theta. Keep, change, and flip. Cosine, cancel, cancel. What's left? 2 sine theta, cosine theta. But what's 2 sine theta, cosine theta? Isn't that sine theta? Sine twice the angle? Isn't this exactly the right-hand side, not the left-hand side? Doesn't the right-hand side equal the left-hand side? And we are finished.